Hello, everyone, and thanks for joining us today. My name is Kelly Quinn Sands, and I'm from NASA Glen Research Center, and I'll be your moderator for today's webinar on shape memory alloy analytics, test data analysis, and reporting. As part of my role at NASA Technology Transfer, I work with NASA scientists who have developed new technologies that may have applications outside of the aerospace industry. We patent these inventions and market them to industry through our website, which I will show you later. Our presenter today is Glen Bigelow. Glen Bigelow has worked at NASA Glen Research Center since 2005. He has been a materials research engineer in the high temperature and smart alloys branch, developing shape memory alloy technology. His focus has been on material design, processing, and applications of shape memory alloys in aeronautics and space. He has led teams to investigate growth of single crystal shape memory alloys, high temperature processing of materials, and development of software for processing shape memory alloy test data. Glen Bigelow has published over 38 peer-reviewed journal articles, 15 conference proceedings, and 1 issued patent. He is active in the technical community in the development of SMA technology and standards with the Aerospace Vehicles System Institute, also known as AVSI, and the Consortium for the Advancement of Shape Memory Alloy Research and Technology, also known as CASSMART. He has received several awards, including the R&D 100 Award, the ASM Engineering Materials Award, and the NASA Silver Achievement Medal. He received a BS in Mechanical Engineering and a BS and MS in Metallurgical and Materials Engineering from the Colorado School of Mines. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box and we will answer them during the Q&A portion at the end. And at this point, I'm going to turn it over to Glen.
All right, thank you, Kelly, for the introduction, and thanks to everybody for attending. And I hope this presentation is very helpful to everybody, and that this software will aid everybody in their jobs and help out with improving shape memory alloy technology. So, like Kelly said, my name is Glen Bigelow. The goal of this whole software that we've developed here at NASA Glen is ultimately we want to be able to use shape memory materials for actuation. And the only way to be able to do that is if we have reliable, traceable shape memory material test data. You know, we have designers and engineers that want to be able to develop actuators, systems, and all of that, and they want to have accurate, valid data. So the driving need, like I said, is reliable data. And firstly, you know, why do we need this? Well, for FAA certification, they go by the U.S. Code of Federal Regulations, which says that the material that's used for parts, you know, which can affect safety, the use of which can affect safety, that data must be established on the basis of experience or tests, and it has to conform to some approved specifications that ensure that the material has the strength or other properties that, you know, a designer would assume when they're designing that system. Other sectors that, you know, want good data and want to be able to use shape memory alloys for actuation include automotive, include space, for satellites and actuators there, industrial valve sector where you're trying to replace, say, like a pneumatic valve with a shape memory valve that is more robust. So, you know, we need these standards for actuator materials. And one of the things that we want to be able to do is look at properties of these materials. You know, we need to be able to ensure that the material that you're looking at conforms to the approved specifications that ensure that the material you're looking at is what you're actually expecting to use. Well, for nitinol, the most common shape memory material out there that's used, that material was developed all the way back in 1962 by Buehler and Wang. Now, a lot of people used it in ways that suited their purposes and maybe their customers, but it wasn't until 2000 and 2001 that we actually had some ASTM standards that would specify how to do testing for these materials. So then we got the DSC standards, which allow you to look at transformation temperatures under no load, and BFR, bend-free recovery, which allows you, again, to look at the transformation temperatures in your material. So you can make sure your material is going to actuate, at the temperature range you want it to be in. But it wasn't until all the way up until 2017 when we actually developed ASTM standards that would allow you to test and evaluate your material in something that's representative of how it would be used in service. And in that case, we have developed UCFTC, which allows you to kind of evaluate the material under thermomechanical cycling, and UPFR, which allows you to kind of look at the material as it recovers its shape, kind of like a standard shape memory test. So, like I said, these type of tests have been used for decades to evaluate SMA properties, and they were only recently standardized. And because they've been used for such a long time, people have different methodologies for how you actually do the analysis. So within the ASTM standards, that methodology is defined, but it's still a loose definition. For example, in ASTM 3097 for UCFTC, the standard says to graphically determine your transformation temperatures by the intersection of these tangent lines. So you draw a tangent line through your transformation, defined by the steepest portion of that curve, and a tangent line through your heating and cooling curves near the LCT and the UCT. And by doing that, you get all your transformation temperatures, your Martensite start and finish, your star point temperatures, which really define kind of the point where the material starts to transform versus these intersections and so on. But, that's all the definition that's there. So when we're trying to produce data for an actuator or for a designer, there's a lot of different areas where this kind of uncertainty can come in, into the data. So how do we reduce the amount of uncertainty in the data? Well, we can look at two different mitigation strategies: reduce the uncertainty or quantify it so that you can deal with it. So ASTM has produced standards for sample prep and design. So we're reducing the uncertainty due to variability in how people's samples are produced. Now we have testing methodology for UPFR and UCFTC, and this helps us to reduce the uncertainty in the test data due to people just kind of running the test in a variety of ways. Now they're more defined there to be able to report it as an ASTM test. We can also quantify the amount of variability that we have, say, from lab to lab by running ruggedness testing and ILS testing. And then finally, we get to kind of the analysis method. And there we have uncertainty due to kind of the method that the data was analyzed with and the actual analysts. People have different preferences for how they kind of fit things and analyze them. And in comes SMAnalytics. That is our whole goal here, is to reduce that uncertainty there due to this. So the big picture here is we have these ASTM standards, we're testing this material, and we want to produce this ASTM certification report, which is defined in the UCFTC and UPFR test methods. So if a customer orders a certain lot of material, they would get this certification report here, defining all the properties of the material, kind of the pedigree and so on. So we also want to be able to put this into something like the NASA Shape Memory Material Database, so that the data can be compared to other people's data around the world. We can look at trends and so on. But you know, we've got this big black hole. How do we get from here, the test data, to the reported data? Well, like I said, historically, people have done, you know, whatever is available to them, anywhere from, you know, plotting the data out, using a straight edge to define these tangent lines, and then getting their transformation temperatures and strains from that. Other people might be using something like Excel. You take your data, define a portion of it, and, you know, fit a line through that. And then, yeah, other people might have custom codes that they've written to define and fit the regions of data. So SMAnalytics itself was designed to fill in this gap and kind of provide a uniform solution to, you know, industry, to customers, to academia, whoever wants it, that can fill in this gap and process the data for you. So right now, in its current form, SMAnalytics addresses 3 common SMA tests, which are differential scanning calorimetry, DSC, and what this test does is we take a small sample from any production stage. So the benefit of this method is you can have a sample from your ingot, or you can have a sample all the way down to, you know, a wire that's going out into a product, and look at the transformation temperatures in it. And that's done by running a heating and cooling cycle and looking at the heat flow in the material. And these peaks here define where the material is transforming from the martensite to the austenite. And this test here is run under no load conditions, which can be a benefit, but also possibly a drawback, as far as you don't need to put load to it, but then you can't evaluate your material under load. So then, to address that, we have uniaxial constant force thermal cycling, which allows you to evaluate your material under load. And this provides kind of the actuation response, and it can be run under some load or no load. And the way that's done is we load our sample, we run a heating and cooling cycle, and then based on, you know, how these tangent lines intersect and kind of the deviation of the curve, we can get our transformation temperatures and our start point temperatures. The third test is UPFR, which is kind of like your, I guess, your classic shape memory test, where you're straining your material by loading it, then you unload it, it's got some residual strain in it, and then you run a thermal cycle to look at how much of that strain you're recovering. And this gives you, again, kind of representative conditions for, say, a one-time actuator, or even a multiple time actuator. But in this case, you can run your thermal cycle stress-free or stressed. So we wrote SMAnalytics to be kind of a user-friendly software. So everything's GUI based. We have a graphical interface there. And the first thing you would see is your launch window. And in this first part, I'll be talking about UCFTC and UPFR because they're very similar. So the launch window allows you to just click on, you know, I want to start a UCFTC analysis or a UPFR analysis. When you come into the software for that, it brings up this window to allow you to select a default profile. And the benefit of these profiles is you can define different profiles for different test types. Say you have a compression test, tension testing, cyclic. You know, if you're running profiles or running test data from different labs, you can have a profile for my lab or for your lab. If you have noisy test data, you might be splitting it up and analyzing it differently. So I can have a test profile that allows me to analyze noisy data, or data that has a fast or slow heating and cooling rate. The next thing that the software gives you is this sample and test information window, which allows you to input kind of the material and test pedigree, so that that data can be output into your ASTM report. So for instance, your sample name, test date, things like the test lab and test rig for traceability, what the material is, it's a warm NiTi, your sample geometry, how you're heating, cooling it. And then there's a part here for notes. So for instance, this material was, aged at 550C for 3 hours or whatever. You can put in kind of all that pedigree data in there. So that'll be contained in the ASTM report and be part of that permanent record for that test data. The software itself accepts a bunch of different file formats and it allows you to easily parse through that data. So when you pull in your data, it'll show you kind of like a preview of what you have, and then you can put in there, my column headers are on line 3 and my first data line is, this line here. And so all that gets pulled in to help you analyze your data or parse through it later. And you can, adjust what type of delimiter you're using in there. The data import is very robust. We can handle raw data anywhere from, your force and displacement data, and the program will actually calculate based on that your stress and strain measurements. You can even have something like a voltage input that's tied to a strain gauge for your data. The data columns that I spoke about on the previous slide, those get automatically transferred over, so you can use your own headers to easily identify which data columns go to which variables, such as your time and stress and strain. And then we have the capability to convert any type of unit to another between American and SI, or standard and SI units, and define what type of output units you want to have on there. And I should say English, but you can define those output units on there and the type of strain, like engineering or true strain. The other benefit here that I want to show you is when you bring in your data, if you have pre-testing or post-test data that you don't necessarily want in your analysis, you can use SMAnalytics to trim that data off. So that can kind of reduce a little bit of your pre-processing requirements. And, this would be a case where maybe you have some extra heating and cooling cycles at the beginning of your test for UPFR. You have like a data spike at the end or beginning, or you reset your strain data in there and you just want to cut out that initial set. So all of that can be done with UPF or with SMAnalytics. Within the software itself, it auto detects these different segments to facilitate your data splitting. So for instance, like heating and cooling segments, it knows, these are at constant stress with a increasing or decreasing temperature. And then the software itself is designed kind of with this whole matrix or algorithm to determine whether a portion of data is a part of a loading cycle or an unloading cycle. And all of this will be on, or all of this is in the user's manual. So if you don't catch things in the slides, they'll be recorded, and then they'll also be in the user's manual that's available. So these customizable filters that we have in here allow you to split up, your clean data, help to account for noisy data such as, load spikes, and then, incomplete data. And they allow you to look at all the different test variables. So we have temperature, stress, and strain, which are the 3 different variables that the software is looking for to be able to split up into these heat, cool, and load, unload segments. We've got a variety of filters on here to help you process your data, and these filters will allow you to help clean up noisy data, for instance. And then you've got all these different sliders and thresholding that you can play with to get the software to split up your data the way you want it to. And so just wanted to mention here, you know, all of these algorithms that are used are mathematically based. It's not just a ad hoc type of analysis. So we're using, you know, derivatives for doing the data splitting, for determining transformation temperatures. We have second derivatives that are used for determining your transformation region and your start point temperatures. So it's all mathematically based, and I'll talk about that a little more at the end here. So once you get all your splitting parameters set up, you can go and kind of preview your data in this results tab. And so the software identifies these key data segments and it'll show you. So you can look at this and determine, oh yeah, it did a good job, or I need to go back and maybe adjust some parameters. So, you know, blues are cooling, reds are heating, and then blacks are load or unload. So for instance, in like a UPFR, you know, again, it shows red for heating, blue for cooling, and then a black with an pointing up triangle or a black with a pointing down triangle to define your load and unload. Lastly, if you have, if you know, just those splitting parameters just aren't working for a specific portion of your data, you have the option to manually go in and use this brush tool to brush your data and select certain data of interest, and then you can, you know, delete a bad split point in there, or add in a manual minimum or maximum or a dwell region in there. So there's a lot of kind of power and customizability as far as analyzing your data. So finally, once you go through all of those settings and everything, well, you don't want to have to redo it for the next test. So you can create a new profile or update the current profile. And what these do is now these profiles contain all those settings that you had in the import settings window and in your splitting window. So the next time you run that same type of test from, say, that same test rig, or even if you have multiple rigs running similar testing, you don't have to go through those again. You might just have to do a cursory glance to make sure it split up things properly. So it'll save you a lot of time for processing your data. Now, when we start to look at the data, UPFR, we start out and we see this load or unload segment, and the software automatically splits these up into between 1 to 4 regions to try to give you the best fit. And, again, like I said, a lot of this software is manually adjustable. So you don't like the fit that SMAnalytics gives you, you can adjust the number of linear regions there. You can take these sliders here and adjust them, you know, to more closely fit your regions. So for instance, you know, here we've got a classic shape memory curve with a loading region. We can adjust that so we can get our slope and our modulus and our yield stress. We can adjust this region here to give us kind of our plateau stress and strain. And then the region for the secondary hardening. And then, you know, we've got this max stress and strain here that SMAnalytics measures. So it'll measure all of these parameters here and spit them out in the final results. As far as the thermal cycle itself, we can look at that. As far as SMAnalytics comes in, it automatically fits your martensite region, your transformation region, and your austenite region. And say you've got a test where, you know, you've got multiple transformations. SMAnalytics can account for that. We can manually adjust these regions here, say to go and look at our first transformation or our second transformation and you know, record that data. The other thing you can do is we've got what's called a data tip here, so we can click on that. We can click on a data point or one of these intersections here, and you can actually look at the numerical data from that and also watch it as you adjust your sliders and see how it's changing, to see how that's, you know, kind of a manual adjustment is affecting your data. Again, we can manually adjust any region or any fit. So here we have SMAnalytics fit to this upper region here, but we'd like to be able to fit to this lower region. Well, we can just adjust those boundaries. And one thing I want to point out is if you have something where you need to fine tune it, you can go over your slider and you can use your scroll wheel to scroll up and down, and that'll fine tune that boundary itself. And then finally for UPFR and UCFTC is we want to get that data out into something like an ASTM report. So we get to our final tab here. SMAnalytics does its own internal check and says, okay, yes, you have a full loading cycle, you have a full thermal cycle, so yes, you can export that to a UPFR ASTM style report. And when you click this export UPFR report, it'll spit out a Excel spreadsheet like this with all your data for that cycle in it. And then it'll also include all this sample info. Now, if you need to adjust something on that, you can click that here and edit that info and then re-export it so that you have all that pedigree and history data in your report. It'll also spit out two plots or a multiple number of plots depending on whether you're running a UPFR or a UCFTC. So it'll show you, you know, all the data that is being recorded and required for ASTM. So your yield stresses, your modulus, your transformation temperatures on here, and so on. You can also go and export the entire database. So, which, you know, we recommend to do because that will record every parameter that SMAnalytics measures. And again, it'll export that into an Excel spreadsheet with all your sample info, and then you know, over 80 different measurements that SMAnalytics records. And it'll also print out a plot of your entire test data, and then say you did something where you did a modification and you have multiple cycles at different stress levels, it'll report out the second cycle at each stress level for you in a plot like this, and a MATLAB fig file. So again, like I said, this software was written to be kind of a really powerful, robust software that can handle not just, you know, a standard test method data set, but, you know, also a data set where, say, you run, you know, multiple stress levels, multiple cycles at each stress level. It'll handle all of that. If we have a test where we have, you know, a high number of cycles, SMAnalytics can accommodate that. Even with, you know, dirty data, you can see like these data spikes, and, you know, we're going to different lower cycle temperatures. You know, SMAnalytics will handle that too. And just for reference, you know, this was a 1,000 cycle test, and it took 3 minutes for SMAnalytics to do it. If I had to do that manually myself, you know, it'd probably take me a couple of days to process all that data down. So that's the power of this software. Finally, we've gone through and we've kind of done validation of this software to look and make sure, does, you know, what SMAnalytics outputs, is it close to what, you know, a human would get for analysis? And so we have, you know, clean data, and, you know, these individual points are manually processed data, and the lines are SMAnalytics data. So you can see for clean data, and even for noisy data, SMAnalytics does a very good job of mimicking what a human operator would do for analysis. And again, you know, everything's manually adjustable. So say you have a certain data point or cycle or whatever that SMAnalytics didn't process very well automatically, you can manually adjust all of that. All right, next let's get into real quickly the DSC analysis. So the methodology here also is to split up each file into cycles and then split up those cycles into heating and cooling segments. And all of this is done automatically. It also goes through and analyzes, where your enthalpy or what your enthalpy is for your test for these heating and cooling peaks, and then your transformation temperatures. And again, all of this is customizable. So SMAnalytics will come in, it'll do a initial automatic analysis of your data. And so you can go in and adjust all of that. And so it gives you a bunch of different options as far as, picking your input and output directories, your output file. We've got a bunch of different manual editing options. You can adjust your, you can edit your tangent lines here, your the fits for your peaks, the number of peaks, all of that. And all that's done between this editing option tree and these sliders here. We can save the data out to FIG files, to a image file, either a PNG or a TIFF file, for you to have for a record, and also to a delimited file for the actual data itself. DScan will detect stuff like, you have questionable data. I've got this DSC test which didn't show any peaks on it. DScan will automatically flag it and say, hey, there's no peaks here. Do you want to, save it as NA? So let's look at, an example. We've got, a complex case here where we've got, DScan has a data set here where we've got multiple or overlapping peaks, and DScan might not automatically catch that, but we can go into our manual edit options and tell it, we want to look at it as having 2 peaks, or we want to adjust, this tangent line here to fit this peak so we can get our austenite start here and our austenite finish here. So DScan allows you all that functionality there. If you have another case where you have, say, these really little peaks here and you've got a curved baseline, so SMAnalytics isn't fitting it, real closely to what we need, we can go in there and we can manually adjust, cutoff points. So we want to cut off the where SMAnalytics is looking at, say, this baseline, at a much lower level here, and more closely fit these peaks. So all of that functionality and capability is there to kind of define these cutoffs, define how we want SMAnalytics to analyze this data. We can also accommodate things where you've got like really weird baselines here. SMAnalytics evaluates this one and it picks this peak here, so, or detects this as the peak. We can tell it, okay, we want to look at this peak here and adjust all the parameters for that. All right, so refocusing on the present here, the entire reason that we developed SMAnalytics and this analysis software is not just for in-house use. We've had software that we've used in-house for close to 2 decades, but we wanted to be able to offer something to the SMA community, for the benefit of all. NASA's kind of tagline or byline there. We're here to help the community to be able to improve shape memory alloy analysis and everything. So our goals were, first of all, we want to establish kind of a uniform analysis methodology. If a bunch of people out there are using SMAnalytics for analysis, and you're reporting it as such, you know that it's been processed a certain way. You know, we want to be able to produce certification data, so a supplier can produce an ASTM report that a customer can then use and say, okay, I know this data is accurate for, you know, my material that I'm getting, and this is what I can use for my design. We want to be able to, you know, accelerate data throughput. Like I said, if I had to manually analyze 1,000 cycles, you know, either it's going to take me multiple days, or I'm going to have to say, you know, okay, well, I'll pick the first cycle, the 100th cycle, and the 1,000th cycle, and then I don't get all the data out that I could possibly get out of that. Again, by kind of using this, we can clarify these property processing and microstructure interactions that we are all looking at for shape memory materials. And the less or the lower amount of variability and variation in our data, we can then clarify what is an actual material property versus, say, you know, noise from how the data was analyzed or from how the test was run. You know, again, that's providing reliable, traceable data. And then all of this, you know, can be used to produce data for, you know, machine learning type of scenario. So a lot of acknowledgments. You know, this data and this software has taken a lot of work from different people, and I'd like to acknowledge the funding from the NASA Glen Research Center through the Aeronautics Research Mission Directorate Transformation Tools and Technologies project that has funded us for a long time through all of our shape memory research and the development of this software. This software was a huge team effort, developed by myself as the lead and Dr. Othman Benifan as the lead for the D-scan portion of it. The primary authors of the software itself were Zachary Toom, Julie Farouche, and Peter Caltagirone, writing the code. And then we also had a lot of contributors, which, you know, without them, it wouldn't have been possible to get to this point. And I'd like to acknowledge Dr. Santo Padula II for the legacy MATLAB framework for analyzing shape memory data, Dr. Ronald Noby, who is the legacy SMA lead, Daryl Gaidosh, who was the helped out with the legacy MATLAB code and methodology, and then Felix Adams, Hector Luna, and Noah Pittman, who helped to write the MATLAB code and to go through all the validation and verification for the software. And I just wanted to point out, if you have any questions, comments, or suggestions on the code, you can email this link here, grc-shapememory@mail.nasa.gov. And if you're using SMAnalytics, if you would please note that you're running SMAnalytics and what version you're using. If you have any you know, bugs that are popping up in the software, or you have suggestions for future releases of it. And this software is available today. You can go download it or go request it at the NASA software portal at software.nasa.gov on this link. And then we also have a user's manual available as well. All right, that's all for me. I'll turn it back over to Kelly and Hia.
Thank you, Glenn. That was really interesting. And I know that we do have some questions that came through in the chat during the presentation, and we will get to those shortly. But first, I'm going to give just a brief overview of NASA's technology transfer process. And again, I'm from NASA Glen Research Center, as is Glenn. And here, if you could go to the next slide, please. So technology transfer has been a part of NASA's missions since its formation. NASA, as Glenn mentioned, is encouraged to share its work for the benefit of all. And in fact, technology transfer is congressionally mandated. And our two primary goals for technology transfer are developing partnership opportunities that promote innovation, NASA technology commercialization, and small business growth within Ohio and the nation. And secondly, enhancing communication and collaboration with industry, academia, government, and other federal research laboratories throughout the United States. Next slide, please. So NASA has 10 field centers throughout the United States. In addition to the field centers, NASA has many installations where highly specialized testing, building of aircraft and spacecraft, and verification occur. NASA Glen Research Center's Lewis Field is located in Cleveland, Ohio, along with the Neil A. Armstrong Test Facility nearby in Sandusky, Ohio. Each field center and installation provide unique services, research and technology to further NASA's missions. Next slide, please, Hia. NASA Glen develops novel technologies in a number of key areas and is the center of excellence for power and propulsion, along with materials and coatings for extreme environments. And as you can see listed here, these are our core competencies. Next slide, please. Glen Research Center patents roughly 10% of all invention disclosures submitted. And our portfolio has over 200 patents available for license. And the Technology Transfer Office has worked hard to make finding NASA's technology easier by creating these industrial relevant categories that you see here. All patented and patent pending technologies from each center are sorted into these categories, which can be browsed or searched on our website, technology.nasa.gov. Next slide, please. And we have some partnering mechanisms, ways to work with us. One of those is patent licenses. We have a lot of technology that is available for licensing. As I mentioned before, we also have software usage agreements. Software is available at no cost, and software is downloadable once an application has been made and the person's identity has been verified. And Space Act agreements. Space Act agreements are a way for companies to hire the government workers to support development efforts. And each one is kind of unique, and there are caveats. Next slide, please. Licensing from NASA is easier than you think. There are three basic types of licenses. The evaluation license, that agreement allows for a test drive of NASA technology. It has a set fee and a set term of 1 year, and it can be renewed annually for up to 3 years. The evaluation license allows a licensee to investigate the commercial viability of a NASA technology with minimal risk. The evaluation license is not a full rights license. NASA restricts the right to sell or offer for sale. Then we have the government use license. That's for entities seeking to use a NASA technology in support of a U.S. government-funded project. These licenses have no fees or royalties, but do have a term matched to the period of performance for the U.S. government-funded project. This license is ideally suited for SBIR, STTR, contract, grants, cooperative agreements, and in some cases, Space Act agreements. This is not a full rights license. The licensee may only use this technology in support of a U.S. government-funded project. And finally, the commercial license. This is a full rights license that is individually negotiated, and these licenses can be non-exclusive or exclusive in the field of use. Next slide, please. And software usage agreements. In addition to our patents, NASA also develops a large array of software codes to support our mission work. NASA makes these software codes available to U.S. entities at no cost. As you can see, the software is organized into convenient and industrially relevant categories to make searching and browsing easier. And NASA transfers executable software codes via a software usage agreement. Software usage agreements contain terms and conditions specific to the release of that code. To search or browse available software, visit software.nasa.gov. And the next slide, please. And finally, Space Act agreements. NASA also partners with industry and academia using the Space Act agreement. Space Act agreements are very similar to cooperative research and development agreements, or CRADAS. They outline the statement of work, specific tasks and milestones, and who is paying for what, data and intellectual property rights, liabilities, etc. Space Act agreements come in two flavors: reimbursable, where the partner pays for NASA's costs to perform the work, and non-reimbursable, where NASA and the partner pay their own costs for performing the work. Generally, non-reimbursable Space Act agreements are used when the proposed work furthers NASA's missions, and reimbursable Space Act agreements are used when the proposed work is in line with NASA's missions but does not help advance it. There are a number of factors that go into making this decision, and Glen's Space Act agreement managers are available to assist in making this decision. Next slide. Thank you very much. And NASA Glen's Technology Transfer Office is available to assist you. Please feel free to reach out to myself or one of my colleagues. And also we have the email there to get in touch with Glen or one of his colleagues about this specific software. And now we can go on to questions. Thank you to everyone who has submitted your questions, and we'll get to as many as we can during the time of our that we have left. And whatever questions we are not able to get to, we will answer via email after the presentation. Does the linear fit procedure follow E3076? If yes, do you have access to the results typically shown in the report requirements of E3076? Glen?
I'm not familiar with that specific standard, so that one I will have to get back to you guys on.
Okay. Thank you, Glen. We'll get back to you on the email for that one. Okay, we have another one here. Glen, with all the adjustable parameters you have have you tried a round robin where everyone gets the same raw data set and processes it with SMAnalytics to see how different the answers are?
So we haven't done a round robin in that sense. I would love to do something like that, kind of like an ILS type of study or ruggedness study. Now, the one thing that we have done is we've taken data from 4 different organizations from the ASTM ruggedness testing and processed it through SMAnalytics to look at the variability between how that specific organization processed the data themselves manually and how SMAnalytics processed it. And then part of that is what I showed in the last slide, talking about the kind of human to SMAnalytics variability, or comparison between the two.
Okay, very good. Thank you. Okay, next question. Thank you for this wonderful work. And this person has a question about DSC data evaluation. Sometimes we can see 2 peaks because of the different transforming phases, such as R phase. How this software handles this type of data. Can it report 2 different TT for a single DSC curve?
Yes, so the software will actually, if you choose within the software to define your curve as a say a 2 transformation or a 2 peak curve, the software will actually produce a in the spreadsheet or in the delimited file that it puts out, it will have a set of data for the first peak and a set of data for the second peak in there for both heating and cooling.
Okay, great, thank you. And here's another question. Are there any plans for future updates or expansions of SMAnalytics to include additional SMA test methods beyond those currently supported?
Yes, so right now we have plans to process data for durability / fatigue. So looking at like very long cycle testing and the parameters that we would be trying to process from the data out of that. And then also we'd like to be able to process torsion data, because a lot of actuators that are being looked at right now are based on torque tubes. So we're planning on having a module for torsion data.
Very good, thank you. And the next question, are there any new types of SMA and can they be 3D printed?
Everybody's, you know, if you look in the literature, people are always coming up with you know, different types of shape memory alloy all the time, and looking at, you know, 3D printing's a very big field right now, and so a lot of people are looking at 3D printing them. And yeah, you know, nitinol can be 3D printed. You know, a lot of different materials, shape memory materials can be 3D printed. So yes.
Excellent. Thank you, Glenn. And I think that, oh, wait, we have one last question, and that's about all we'll have time for. So I apologize if I didn't get to your question. We will answer it via email. And here's the last question, Glenn. Considering the significance of standardized testing methods, how does SMAnalytics ensure consistency across different labs or testing environments?
So one of the ways is, you know, through the kind of validation and verification that we've done by, you know, processing data from different organizations through SMAnalytics. Like I said, I would definitely like to see something like a ILS kind of round robin testing of SMAnalytics and evaluation. But, you know, as I said, there's a lot of data out there and a lot of types of data, and the benefit that SMAnalytics gives you in being able to manually adjust things, you know, also, you know, it's hard to standardize some of that, but I would like to look at, you know, the kind of some more verification of the software itself. So, you know, each person that downloads it can also act as an evaluator. You know, we welcome feedback, you know, as far as if it's doing, you know, what you expect it to, you know, and if there's any other capability that you would like to see.
Excellent. Thank you so much, Glenn. And that's about all the time we have for questions today. And again, if we didn't get to your question, we will follow up with an email within the next week. And if anyone thinks of any additional questions after the webinar today, you can contact Glenn and his team at the email shown here or at the QR code that you see on the screen. And once again, we really appreciate everyone taking the time to join us today. And thank you, Glenn, for taking the time to do this webinar today.
All right. Thank you.
Have a great day, everyone.